Good morning, students. So let's see what unit to have, and let's have a explanation on this second unit. So second unit starts with the conventional encryption principles. So what it says is, so here in this you'll be learning the symmetric encryption, and also referred to as the word here conventional encryption. You'll be using a secret key or the single key encryption uh, prior to the development of the public key encryption in late 1970s. So first you guys have to learn what is this symmetric encryption. Later you can go with this public key encryption or symmetric encryption. So what is this symmetric encryption is? It has five ingredients, students. First is the plain text, the message that you want to send from the sender to the receiver or the source to destination. This is the encryption algorithm. It performs various substitution and transformations on the plain text to convert the plain text to the ciphertext. Third one is the secret key. So this key is used to make the substitutions and transformations mentioned in the encryption algorithm. So how you are going to do that? That is done using a secret key. Next, ciphertext. So after actually doing this substitutions and transformations, the obtained text is the ciphertext. Decryption algorithm. So this is essentially the encryption algorithm run in reverse. It takes the ciphertext and it produces the plain text using the same key. If you are using the same key, then it is the symmetric encryption algorithm. So this is the diagram. So plain text. So X is the input given to the encryption algorithm. So parallelly, you are giving the key as well. So this is the key, students, and then this is once you get the ciphertext that is transmitted over a network. So what is this is ciphertext? Y is equal to E of k comma x. That's what is written here. What is Y is the ciphertext. Okay, and once this Y is reached to decryption algorithm, so Y is the input for decryption algorithm, and the same key that you have used here is provided as an input for this decryption algorithm. It produces the same X. So what is X is D of k comma Y. So that produces the plain text. So security encryption depends on the secrecy of the key. This is the line that I was stressing in the class. So how many procedures or how many substitutions or transformations you do, students, the main secrecy lies on the key. The key is known to the hacker, then it's a waste of doing all this procedure. Okay, next, cryptography. So this is the definition of the cryptography is a technique of securing information through the use of codes so that only those persons who is intended can understand and process it. It is classified along three independent mechanisms, students. So I'll be explaining you three. So before that, crypt means hidden, and prefix crypt means hidden, and suffix graphy means writing. So this is what you have to understand. The definition came of this prefix and suffix. So now let's go to the three independent mechanisms. What are they? The types of operations used for the first one is the types of operations used for transforming the plain text to ciphertext, and it has two general principles. One is the substitution. So what substitution is? Any character in the plain text from a given fixed set of characters is substituted with the other character from the same set depending upon the key. Suppose we say like the shift 1, A would be replaced by B and B would be replaced by C. So this is the mathematical representation. A equal to 0, B equal to 1, so on, Z equal to 25. That is how you initiate the numbers from 0 to 25, total 26 alphabets. Encryption of a letter by shift n can be derived as, so this is a representation. So encryption is x plus n mod 26. So why do you make this mod 26 is to make sure that whatever you are getting is you are getting in this alphabet set only. That's why you actually make this modulus. What is decryption is x minus n mod 26. So encryption is nothing but you are going to transform, that is x plus n. Decryption is nothing but it's the reverse of the encryption. So once you make plus here, you make minus here. So this is the figure like A, B, C, D, E, F. A is getting transformed to D, B getting transformed to E, C getting transformed to F. That is about the substitution. Now let's go to the transposition. It's a type of encryption technique where the position of the letter in the plain text are rearranged to form a ciphertext. So substitution is you're actually transforming that original to some other text. Transposition is you're just transforming, but the original text will be there, but they are rearranged. So so here one will be exchanged with 3, 2 will be replaced with 1, 3 will be replaced with 2. That is the same text will be replaced like this, the diagram that it is shown here. Now, what is this rail fence transposition cipher? It is, suppose say hello Krishna. So the key is 1. This is the plain text. Key is 1. So you just write like HELLOKRISHNA, right? Now the ciphertext would be HLORSNELKIHA. Okay, this will be the ciphertext. Suppose geeks for geeks, the number of ratio is 3. So how did you write it? GEEKSFORGEEKS. Now, how do you write this? GSGS, then next row, EKFREK and EOE. Okay, this is how, this is, what is this? This is a rail fence. And next, the number of keys used. Both the sender and a receiver use the same key, then it is called symmetric. If they use a different key, then it is called asymmetric or the public key encryption. This is the second one. Right? And third one is the way in which the plain text is processed. So first is the block cipher. The process one block of elements produces output one block. Stream cipher processes the input elements continuously, producing output one element at a time. So how is that you want to do? So these are the 1, 2, 3 students, like we were actually telling it here, 3 independent mechanisms. First is the types of operations. Next is number of keys used, and the way the plain text is processed, whether either block or stream. Now, block transposition cipher. So notes, you can just directly go to the example. This is the explanation of the block transposition cipher. You can just directly go. So this is the example I made you guys to write in the note, students. So first, this is the plain text. Meet me at the bridge at noon. Keyword is secret. First you sort it, students, in an alphabetic order, that is lexicographical order. Once you sort it, right? So secret, you just write secret and you just write meet me at the bridge at noon. So this is empty. That this empty can be left as it is, or it can be replaced with a character that is not present in the plain text. So I have replaced with ex here. Okay. Now, once you get the columns, no, these are all the columns that you get, students. So what you do is you just arrange this. So you get CEERST. Now CETDOE. I'm taking this E first. There are two E's, right? So if you're taking this E also, it is totally fine. Okay. So what is transposition? The main target is to rearrange the original text. Okay. Now MEN, I'm taking next ETINRTHGO. Next yes, MART, again TEBAX. Okay, so after that, now you write EMETME like that. So you'll get a text. This is the ciphertext obtained after first transposition. Now the second transposition, students, you use another key. You are using two keys here. Okay, other key is cipher. Now you just rearrange that in a lexicographical order, that A to Z. Okay. Now, once you get that, first write cipher, and whatever the text you got here, right, you just write it here. And after that, again, you just rearrange. Okay, once you rearrange, you'll get it. So, but here, students, if you just observe here, observe this, CEHIPR, I've just written correctly. So, CETDO, correct? Next, E. E is here, MART. I should have written, okay, I should have written like MART here. And next, H, THGO, I've written this correctly. Next, MEEN. So, MEEN should come here. And next, P, ETIN should come here. And next, R is EBA. This one is correct. So what this one, you just make a correction, students. I think you have written correctly in your notes. I just gave an example to you also to make you practice this transposition. Okay. Now once you get the ciphertext, this will be considered as the final ciphertext. Okay. And the ciphertext is much more secure than the singular column transposition. Singular column is once you write the text after the first one, right? This one, you can consider this as a ciphertext. If you feel like no one is able to decipher it, you can consider this. But doing one transformation is not safe, right? So better go for double transposition. The next important, the algorithm that you guys, the first algorithm that we have discussed is the data encryption standard. It is a symmetric block cipher developed by IBM in 1970 and later standardized in US. And the key features are it contains a block cipher of 64 bits, key size of 56 bits, symmetric encryption. It contains 16 rounds of encryption and decryption, Fistel network. So during the encryption, students, there is a Fistel network that is also processed in 16 rounds. In the Fistel network, you contain permutation, substitution. They are called as S boxes and P boxes, the initial and final permutation. So these are the key features. So D is symmetric encryption algorithm that scrambles data to keep it secure. So to keep it secure is that it is the plain text. It works with 64-bit and uses 56-bit key. Right? Now convert the plain text to binary. So this is the plain text example that I made you to write. I convert that into binary. So for DES, we need 64-bit block, right? So once you write this one and this one in an order, this is what you are going to get. All the others are added with zeros, right? Now starts the initial permutation. DES rearranges the bits using a predefined table. Okay. Now what I have done is here I have just written in an 8 by 8 matrix, students. So all these 64 bits should be written like here it will come like 0, 1, 0, 0, 1, 0, 0, 0. Okay, and next one 0, 1, 1, 0, 1, 0, 0, 1. Okay, so these first 16 bits will be this students, and other all 64 bits will be zeros. What you have to do, you have to rearrange, shuffle this. Shuffle means like, so here there is a 50th bit, that is 0, that will come here, right? And 50th bit, which is here, That will be the second position, right? If you just see the source students, I think it's 58 here, somewhere here, 17 here, that will be like that. But I've taken the liberty of rearranging it. Okay, next. So after applying, once you start writing, like you'll get zeros and ones in this position. This is 50th position, this is 50th position, right? You'll get a text. After this is the resultant of the initial permutation. Okay, now generate 16 round keys and DES takes 56-bit key and creates 16 different 48-bit keys, right? So how do you get 58-bit key is, so key is also like 64-bit, right, students? So what you're going to do is you are going to discard every 8th bit. Once you discard every 8th bit, students, so that 64-bit will become 56-bit key. Okay, so that's how you actually generate. And 16 rounds are actually explained in 7 steps. So first you split those 64 bits to 32, expand the right half to 48 bits, XOR with round key, pass through S box, permute the result, XOR with the left half, swap the halves, that is left and right will be swapped. So this step you are going to understand in a diagram in the next page, right? These steps are repeated for 16 times, students. So you will get a text after repeating 16 times. You are going to get a text. That text again, you are going to permute one last time. Okay, the final block is again permuted again in the final permutation, and the obtained text is the final ciphertext. So here the input is high, the output you are going to get it like this, students. High is actually presented like this, right? Now this is the block level steps for DES. Understand this: 64-bit plain text, you are going to pass it to the initial permutation. So once you get the initial permutation, left plain text and the right plain text, students, 32-bit. So you are going to make this left plain text and right plain text pass through 16 rounds. And obviously for the plain text, the input is the plain text and the key, students. So you're going to provide the key, the left plain text and right plain text. And finally, you are going to get one text here. You are going to do a final permutation. And once you do the final permutation, the obtained text is considered as the ciphertext. Okay, so this figure, key transformation, expansion, S box, P box, and XOR and swap. The steps that we have discussed here, right? So broadly, like first is the key transformation, next expansion permutation, S box permutation, P box permutation, and XOR and swap. So the basic steps, the broadly how the steps are there in DS, broadly explained and shown in this diagram. Now, this is the diagram that I'm stressing on, students, which you guys have to understand. So plain text 32 bits, 32 bit, students. This is left half, this is right half. Only this right half is sent to the F box here. Okay, in F box, you have this S box and P boxes here. Okay, now first, this 32 bits is sent to the E table, students, right? This 32 bits, right? So this E table transform this 32 bits to 48 bits here. Why 48 bits is, see here, this XOR has two inputs. One is the output of the table, and next is this from the key. You are getting 48 bit. So here, now let's see this one. This one, students. The key, that 56 bit, right? So 64 bit, once you discard every 8th bit, you are going to get 56 bits, right? Again, that is left and right. Since you have written as L and R here, that they have written like C and D here. Why Ci minus 1, Di minus 1 is that I actually represents the number of rounds. Okay. Now 28 bits and 28 bits, right? You are going to left circular shift, the left circular shift, right? So once you left circular shift it, you are going to get, and here you are going to transform those bits into 48 bit. So this 56 bit is transformed to 48 bit here. Since the output of this C table is 48 bit, you are making the key size, compressing the key size from 56 to 48 bit here. So 48-bit XOR will be sent to S box. Okay, this is a substitution that happens here. Once the substitution happens here and the output is 48-bit, you're going to do the permutation here. Once you have done the permutation, the output is XORed with the left 32 bits here. So here this one will change this 48 bits to 32 bits here. Okay, so 32 are XORed here, right? You are going to get a result left and right here. And for the next round students, you are going to swap left and right. Okay, once you swap, you'll get 32 bits here. Again send. Again, you are going to give the 48-bit key here. Okay, so that's how the DES actually performs the encryption, and this table, this diagram should be repeated for 16 times so that once you get that, you'll get the ciphertext, and finally you are going to perform the final permutation one more round. Then only the obtained text is considered as the ciphertext. Okay, so this is what I have explained here in this. So once you understand the diagram, that is enough for students. So here I have explained the left shift two positions. What is this? And here CI is left shift and DI is left circular shift, and key is the CI comma DI PC2. This diagram. Okay, CI comma DI. Uh, and yeah, RI is left 32 bits XOR and F of RI comma KI. So this one is shown here. LI XOR RI comma KI. Okay. Only right one is sent to the F box here. Okay. So next is, so after, students, like this DES, though we perform 16 rounds, the ciphertext that we have written here, right, for the high, okay, this one can be deciphered in 22 hours. Okay, so just understand the complexity of it. Though it is complex, your uh, plain text is getting deciphered by the hackers. Okay, so next algorithm is blowfish. So blowfish is an encryption technique designed by Bruce Snare in 1993, and it is also a symmetric block cipher algorithm. The block size is 64 bits, key size is 32 to 448 bits, and number of subkeys you generate is 18, and number of rounds is 16, and number of substitution boxes is 4. So this you are going to see in the diagram. So 64-bit plain text, the output is 64-bit ciphertext. So total number of rounds, like it is 16 here. So 0 to 15. For every round, you are going to give the keys 0 to 16 keys, 0 to 15, right? They are kept in an array, right? Again here, once you get, after processing 16 round students, again, you are going to do the one more round, the final permutation. It is just like the DES, right? So here is the step one is generation of the subkeys and initialize the S boxes students. And step three is the encryption. Encryption function consists of two parts. So like DES, see here, this is 32-bit, right? 32-bit left, 32-bit right. Okay. Now you are going to XOR with 32-bit PI. Okay. Now this is the key here. So you're going to send that to the F box. The output of it is again XORed with right? And this is considered as left, and this left is considered as right for the next round, students. So this process will be repeated for 16 times. So encryption consists of 16 rounds. That's what I mentioned here, right? And what is decryption? Right? I told you, like, there are 4 X boxes here. So like we mentioned here, number of substitution boxes is 4, right? So 8-bit XA, 8-bit XB, 8-bit XC, 8-bit XT. SBox 1, SBox 2, SBox 3, SBox 4. Right? Now, the output of it, you are going to add these two. The output of it is again XORed with box 3. The output of it is again XORed with box 4. Right? Finally, you are going to get 32-bit output. Right? So the flow diagram of F. So here, what is this F? What F performs here is the students, right? And the addition here is always a modulo of 2 power 32, so that if you get what we have discussed in the class, like if you get any carry, that will be discarded using modulus. And post processing here, 32-bit XL, 32-bit XR after performing 16 round students XR. So here in the diagram students, here there are 16 keys, but what you have mentioned here, 18 keys, right? So that last two keys, 17, P16 and P17 are used here. 32-bit XL, the 32-bit obtained ciphertext is again is added with 32-bit key 16, and 32-bit XR, the right half, is again added with uh, P key 17, and once you get it, you just exchange these two. XR will become XL, XL will become XOR. So whatever the text you get, right, that is considered as the ciphertext. So this is Bluefish. Next, idea. So international data encryption algorithm. So it is an encryption option for converting the plain text data to unreadable format, obviously. It is a symmetric key block cipher developed by Zuzelia and James Massey in 1991. Block cipher idea operates with 64-bit plain text and ciphertext blocks and is controlled by 128-bit key. It uses a series of mathematical operations including modular, arithmetic, bit stuffing, and exclusive OR operations to transform plain text to ciphertext. The algorithm is fast and requires a small amount of memory and processing power. So this is the line that we are mentioning for idea. So block cipher structure is the plain text block size 16 bits divided into 4-bit chunks, and key length is 32 bits. The output is obviously 16-bit ciphertext. So mathematical core operations, XOR, addition modulo, and multiplication modulo. Okay, this is plus, this is asterisk. So input plain text. So 16 bits, 16 bits, 16 bits, 16 bits. You are going to use key 1 to K1 to K6. Next, round 2, round 3. Okay, so on. So here, this is round 8. So you will get K43 to K48. And once again, the output transformation K49 to K52. So the text that you are going to obtain after all this is the ciphertext. Okay, in each round, 6 subkeys are generated. Each subkey consists of 16 bits, right? So here 16 bits, 16 bits, 16 bits, 16 bits, 16 bits, right? And there are 8 rounds in idea. So here 8 rounds in idea, and each involve a series of operations of 4 data block with 6 keys. So 4 data block with 6 key students. So 1, 2, 3, 4, 1, 2, 3, 4. So this round I've just mentioned it as a round 1, 2, 3, 4. I'll tell you like 6 keys, right? Key 1, key 2, key 3, key 4. The other 2 keys I'll tell you in the next diagram, students. Each involves series of operations of 4 data block using 6 keys. These steps perform a lot of mathematical actions. Uh, these are multiply, add, XOR operations. Multiply means multiplication modulo, add means addition modulo. So these steps I made you to write in the class, students. So first you are going to multiply P1 and K1, add P2, K2, add P3, K3, multiply P4 and K4. So step 1 to step 4, you can obviously write. The problem is like step 5 to step 14. So you have to mention these operations. So if you just see step 11, this is the XOR, 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 right? And here you are getting two XORs, multiply, multiply, add, right? So if you can just remember this. First two are XOR and last four are XOR, right? In the middle, you are get the alternate multiply, alternate add, right? And remember, like step 1, 2, 5, 6, 8, 7, 1, 3, 2, 4, right? Step 1. And here 3, 4, 5, 7, 6, triple nine, double 10. So this is very simple to remember. This you should remember like a phone number here. 1, 2, 5, 6, 8, 7, 1, 3, 2, 4. 1, 2, 5, 6, 8, 7, 1, 3, 2, 4. So this one 3, 4, 7, 6, triple nine, double 10, right? So this one, students, this is the diagram, the sub key generation. So from 128 bit keys, these 52 sub keys are generated, right? So each having 16, right? So total 832 bits. So 128 bit to 832 bits, right? But we have only 128 bit. How it is possible? You see here. Key 1, 1 to 60, 17 to K2 is 17 to 32, K6 is 81 to 96, and unused is 97 to 128 students. These are the remaining unused. For the next round students, so 97 to 112 will be K1 and K2 will be 113 to 128. So all the 128 bits are used. Okay. Now you have to circular shift by 25 bits, the original 128 bit key. You'll get a new 128 bit key. So key 1 and key 2 for the next round are already there. You should worry about the key 3, key 4, other key strings. So 1 to the new 128 bit key you are going to get, right? So in that 1 to 16 will be K3, 17 to 32 will be K4, and like that you're going to do the circular shift, students. Again you will get unused bits. So unused bits will be again used for the remaining unused will be used for the key for the next round. That is how you generate. You have only 128 bit key, but you are going to generate 832 bits, right? So finally, this is the output transformation. This is a one-time operation, students. K49 to K52 are used here. So step 1 is multiply R1 and K1. Step 2 is add R2 and K2. Step 3 is add R3 and K4. Step 4 is multiply R4 and K4. Out of performing all these operations, you are going to get the final cipher text. So by this, you have seen what is idea, and next you have seen what is a blowfish, and you have seen what is DES. So these three are very important, students, because these are the algorithms which actually tell you how the encryption actually is performed. And cipher block modes of operations. So block cipher modes of operations define how to securely encrypt and decrypt large amounts of data using a block cipher. Okay, so there are different modes, students. So first mode is electronic code book mode, ECB. So P1, you pass the plain text to the encryption algorithm with the under input key, you'll get the cipher text. So likewise P2, K, you'll get C2. PN with input K, you'll get CN. This is the encryption. Likewise C1, you pass it to decryption, you get the same plain text. So here each block is independent of each other, right? So that's the advantage, because you can actually do the parallel processing here. Parallel encryption of block is possible, and message in bits is broken into bunch of blocks, right? This is the advantages. And disadvantages is this, it's prone to cryptanalysis, because identical plain text blocks produce the identical ciphertext. So the example is like if you have the plain text like GRIAT, 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 right? So the same GRIAT will produce the same ciphertext. So it will be easy for the hacker to identify what is the original plain text. Okay. And next is cipher block chaining. Uh, Previous cipher block is given as input to the next encryption algorithm. Now here, since we are saying like each block is independent here, right? That's an advantage for parallel processing, but that will become a disadvantage here for the hacker. However, you may do, students, you got to see that the obtained ciphertext is not identifiable to hacker, but problem is same plain text is producing the same ciphertext, right? So the next is it's not independent. Every round is connected. So P1, uh, you are going to do the XOR and with the input key encrypt, and you're going to get the ciphertext that is made XORed with the plain text here. So you can take some random text here, students. Right here, the input is for the XOR P2 and C1. Do the encryption, you'll get C2. Right? Everything is connected here. Likewise, whatever the operations you do here, you do the same reverse for the ciphertext. You're going to get the plain text. So it is better than the previous one, ACB. CBB works well with input greater than the B bits, and this is very difficult for the parallel processing. That's a disadvantage. The very basic nature of this is we cannot perform the parallel processing, but that is actually made as the disadvantage here. Yeah, that is you cannot do the fast processing, students. Next, cipher feedback mode. This is a feedback to the next block of encryption with same new specifications. So initial vector, you do the encryption with key, you'll get S bits. So the final bits that you are going to get here, the bits that you are going to get here, divided into S bits and B S bits, right? In this, you are going to select the S bit, students, and give it to the XOR with the plain text. You'll get the ciphertext here. What you are going to do with this is you are going to discard here, right? See the next round here. This ciphertext goes and you are going to do the shift and you are going to get some bits. So this will be BS bits and S bits, right? You are going to swap and you're going to do the encryption. And once you do the encryption, students, with the key, you're going to get S bits and BS bits. What are you going to do here? Discard this BS bits. With the only S bits, you're going to do the encryption with P2 and you'll get C2 here. So this process goes on until you complete the complete plain text, right? So here, whatever you do here, you're going to do the reverse, right? So S bits is the number of bits fed back into the shift register for the next encryption. The remaining remaining bits are shifted out and discarded in each iteration. Okay, discarded. You just remember this word, discarded. Encryption process uses an initialization vector, which is encrypted using a block cipher. First S bits are encrypted and XORed with the first S bits of plain text to produce the ciphertext. Ciphertext is then shifted to the shift register, replacing the old S bits while keeping the remaining BS bits. This updated register is used for the next encryption step. The process repeats for the entire message. The same diagram, this diagrammatic explanation is given here, students. And the output feedback mode. So it follows like the same, like cipher feedback mode itself, but all the S bits of the block are sent instead of sending the selected S bits. So since you are saying like this B S bits will be discarded here, right? So there is a chance of data loss. Since there is a chance of data loss here, so the output, you are going to get some bits here, right? Instead of dividing them S bits to BS bits in output feedback mode, just don't divide, you just give that to XOR with P1, you're going to get ciphertext. And here no shift register, just pass that to the next round directly encrypt with the key, you're going to get, and this is XORed with the P2, you're going to get the ciphertext here. Okay, so do the reverse here, you'll get the decryption. So advantage is OFB is free from the bit errors. Disadvantage is if key stream is reused and security is compromised. So that repetition should not be there. Like in the first mode, like you, if you have the same plain text, you'll get the same ciphertext. So if you have the same key stream, the security is compromised. It will be easy for the hacker to decipher the plain text, right? And next topic is location of encryption devices. So how do you ensure in a whole network, how do you ensure to keep the encryption devices? So this is the sender, this is the receiver, this is the receiver, and this one, whatever highlighted here, these bubbled ones are end-to-end encryption, students. And here, this in the middle, I've just kept some, these are all the devices, encryption devices. These, all these things, these are link to link encryption, right? Link to link encryption. Okay, so here this diagram says is like you're going to send the data here and you have this PSN, right? So packet switch node, right? So packet switch node, packet switch, right? This guy has to know whether the packet that came to here, this fellow has to redirect the packet to this direction or this direction, right? So here the first one is end-to-end, students. Once you encrypt the data here, here only you are going to decrypt. Here only you are going to decrypt. Okay. The end-to-end is here you are going to encrypt. Before this fellow gets the data here, you are going to decrypt here. Why you are going to decrypt is because this guy has to know from where the packet came and for whom he has to send. Okay, the addresses he has to know, right? That's why you are decrypting here. And once the packet is sent, it is encrypted here, again decrypted here. Again, this guy has to know. Likewise, here, if the packet is sent like this, it is encrypted here, it is decrypted here. Because this guy has to know to whom the packet should be sent. Okay, so here link to link encryption devices are there and end to end encryption devices are there. Okay, and finally, you are going to achieve greater security with both link and end-to-end encryption. Okay, so next is the key distribution, students. So I'll just directly explain the, so here, see here, key distribution topic starts here. Okay, the next page should be this actually. So notes also have written it like that only because I have this empty space in the page. So key distribution center, the host actually requests. So KDC provides one-time session key for the connection. One-time session key is that session will be live for some seconds. So for those seconds only the key will be live. You can do with the communication. You can transform the data. Once the session is done, students, key is lost. Right? During that session only, you got to see that you are transforming the complete data. So step one. So here, just understand 1, 2, 3, and then 4. Just 4 steps. When the host wishes to set up a connection, it transmits the connection sequence packet. Okay. He requests. Host will request. That request will go to FEP. FEP saves packets and applies to KDC for permission to establish a connection, and this communication is encrypted, obviously. So once FEP receives the request, right, that FEP goes to the KDC. Here is an FEP, that request goes to the KDC. So step 3 is if KDC approves the connection, it generates a session key and delivers to two FEPs. So once the request is made to KDC, students, KDC will actually review the request, and once the request is approved, a session key is generated from the key distribution center. The requesting FEP can now release the connection and all the used data exchange between the two end systems are encrypted. So once the key is approved now, students, so here you can actually send the data over a network. Okay, so this is the key distribution center. Just remember four steps here. So this completes the first half of the second unit, students.